Okay, so our next speaker is Johann Rosain, who'll speak about bounded sort polymorphism. Thank you very much.
Okay, thank you. So, yes, today I'm going to speak about bounding sort polymorphism so that we can actually use it in real life, right? And so, yeah, but before that, I'm going to open a small parenthesis about, we are all computer scientists here, and we know that some of us can be very opinionated, like Stephanie said in her talk an hour ago, like some people will defend type conversion with their body, and others will swear by untyped conversion, right? And, well, even if we are mostly a very opinionated community, we more or less agree on one point, that code duplication is harmful, right? Or, it's been put much more elegantly than I can say in this book named Principle of Programming Languages, which reminds me of something, but I can't quite put the finger on, right? Or also said very concisely by Dijkstra, saying, 2 or more, use a 4. Very nice, right? And so this is, programming languages have been evolving to avoid this kind of duplication. Even imperative languages have something like higher order functions or even polymorphism, right? But at some point in the evolution, there was a divergent path where multi-sorted type theories arrived, and there, duplication was somehow, well, okay, I don't know why, right? So first, yes, what do I mean about multi-sorted type theories? So usually, we have typical Martin-Löf dependent type system with dependent functions and a hierarchy of universes of types, right? And we can even add inductive and records, their elimination rules, introduction rules, projections, and so on. But in multi-sorted type theories, instead of having this whole type hierarchy, what we have is universe hierarchies, where they are parameterized by a sort S, which is in some kind of set G of ground sorts. So this set of ground sorts, we say that what we want to have is a distinguished sort type for which, well, we can type other universes with at the next universe level. We also have predicative sorts and impredicative sorts. By impredicative, I mean that the universe, we only care about the universe level of the codomain when doing dependent function. So, yeah, this is actually a model that quite naturally models current proof assistants. Like, for instance, we have Agda that has 2 predicative hierarchies of set and prop, Lyn that has 1 predicative hierarchy type and 1 impredicative hierarchy prop, and Rocq that has also some same stuff as Lyn but with SProp. So this is nice. We have multiple hierarchies to mean multiple things, like, for instance, with types or sets. Well, we have computational contents, we put Booleans in it, integers, natural numbers, and so on, and we also put, well, types, right? And in prop or SProp, we can have proofs sometimes irrelevant. So this means that basically we can't just pass from one hierarchy to another. We have to have some kind of restrictions because, for instance, we don't want to produce computational content from maybe irrelevant proofs. So here, what we say is that, okay, we cannot say, yes, well, what I just said, right? But in practice, what this means is that this kind of stuff leads to duplication. So why is it the case? Well, it's because, for instance, if you want to write a sum type, you can say, I want everything to be computational, right? And so you write it like this. But yeah, maybe you want to write a logical disjunction, and in this case, you want everything to be propositional, and you write it like that. Or, well, you could do a mix of both, saying, okay, I want my sum type to be computational, but I don't care about the values it has, and you say, oh, I have some stuff that is propositional and some stuff that is computational. And so this is actually examples that we can find in Rocq standard library for more than 20 years, right? Okay, and so last year at POPL, there was this magnificent paper saying, okay, we can avoid duplicating such inductives. So how do we do that? Well, instead of having sorts, static sorts, we can quantify prenexly over sorts and say, for instance, we have A that is in the sort SL, B in the sort SR, and the target sort is S. And so using this, yeah, okay. So this basically makes all the previous combinations of all the different sorts. And yes, so here maybe the annotations are a bit scary, right? But okay, so on the right we have universe levels that I won't use anymore in this talk because it's totally orthogonal to what I'm going to be talking about. And what we are going to focus on is sort level polymorphism that is on the left of the brackets here, okay? And so all of this is universe polymorphism, but yeah, we are only focused on sort polymorphism here. But the problem is that even with this, we can't avoid duplication. This is not enough. And why is this the case? Well, for instance, we can have an even more scary term for the eliminator of this generic sum type. Here, we have U that is a sum type in the sort S, and we want to create a content in the sort S prime. Okay, so we quantify over all of these sorts, and we write this term. But if this was accepted, we could instantiate, for instance, S with prop and S prime with type. And if we did that, then we can now create computational content from proofs. So the very stuff that we forbid at the beginning because it would make everything consistent, right? And yeah, I mean, we could also say S is instantiated by SProp, and we have an even simpler proof of fault. So what this means that now we have to declare all the valid eliminators by hand, which is as bad as it was before. Like, yeah, we have hidden some of the stuff, but it comes right back at us, right? And so there is also another problem of prenex sort polymorphism as it was presented last year, is that in the system that's sort poly, I refer to it like that now, there is no principal sort assignment for a very simple term that is a mapping between two lists. Because here, so in Rocq, we have that the lists, we have the type, we can create everything from types. So here, if list A lives in type, then you can create a list of B. But maybe list A lives in the same sort as list of B, and so it can also create a list of B. And so there is no instance that supersedes the other, and so yeah, this is, there is no most generic sort assignment for this term, right? And so what we did is to introduce bounds in this sort polymorphism system to allow writing the most generic terms, so basically to have terms with the principal sort assignment, and to infer these terms so that we don't have to put all these scary annotations of the previous terms. So we show that it has relative consistency with respect to the sort poly system, and actually it has the same logical power. So yeah, in this talk I'm going to focus on explaining a bit about the relative consistency because yes, it shows some hidden properties of the system. Okay. And so what we propose to bound sort polymorphism is to add elimination constraints between sorts. So here, when we want to define the most generic eliminator for the sum type, well, we say, okay, we want S to eliminate into S prime. So here, we call that S is the sort of the sum of the term of the sum type that we want to eliminate, and S prime is the sort of the type we want to create. And so if we say, okay, we can now create elements from the sort S prime from elements of the sort S. And so this term is type checking. So yeah, I mean, elimination constraints between sorts is something that is also pretty natural in current proof assistance. I mean, for instance, in Rocq, there was this table of elimination between sorts. And yeah, I mean, this is a natural extension of the theory. And we can see that in Agda, well, we have these elimination constraints like set eliminates to set eliminates to prop eliminates to prop. And we can do more or less the same stuff for Lynn and Rocq. Yes. Okay, but so this is very natural, but actually it induces some strange stuff. So for instance, if we have sort S, such that SProp, so which is proof irrelevant in Rocq, so that SProp eliminates into S, we can prove that S has propositional proof irrelevance. But better, we can actually show that it has definitional proof irrelevance. So how do we do that? So assuming that we have a type in the sort S and X and Y, two terms of type A, well, we want to show that X is Y. But actually, we can define a function that takes Booleans in SProp and returns values of type A. And we say, okay, if the Boolean in input is true, then we return X. If it's false, we return Y. And what we actually have to prove now is that f of true is equal to f of false, because f of true is X, f of false is Y. But here, because SProp is proof irrelevant, it means that true is actually definitionally equal to false. And so we can just say but it's reflexive, right? So here, X is definitionally equal to Y, which means that when we have such elimination constraints, for the type checking to be correct, we have to inherit all the conversion rules of the sort that is above. Okay. And so this is kind of the hard part of the consistency theorem. So here, we assume that the system of sort poly is consistent, and then we show that there is no closed term of type bottom in a consistent sort. So maybe this sounds like a tautology, but yeah, actually, it's not really a tautology. And also, yes, there is in this statement, there is no notion of the ground sorts G when we say, actually, we work in a system with abstracted ground sorts. So this hides some things. So yeah, why is this not a tautology? It's because actually what we say is not, I mean, we say that S is a consistent sort when S eliminates to a ground sort that is assumed consistent, like SProp or prop or type in Rocq, not when there is no proof of false in it. And yeah, so we will see that this theorem holds if we have some conditions, of course, on the set of ground sorts. So let's talk about these conditions. So what we want to do is that if we have a closed term T of type bottom in the sort S, we want to instantiate away the sort variables so that we get a term without elimination constraints and a term in sort poly that is, well, of type false. So the question is, but how can we do that? Well, the first answer is to say, maybe we can have some kind of initial sort that I name data, which eliminates into every ground sort. And with this, we say, OK, we instantiate every S using data. So this approach doesn't work because, well, of the conversion rule inheritance that we saw just before. What if at some point we have to instantiate a sort at data, and, well, actually in the typing rule, it used the conversion rules of SProp. I mean, it's not possible anymore. So seeing this, we can say, OK, maybe what we have to do is to instantiate every sort using the ground sort that's directly above it in the elimination hierarchy. I mean, yes, this kind of works, but actually not alone. We need conditions on the set of ground sorts. So first, this sort that's directly above S may not always exist. Like in this case, well, we have a sort S prime, such that SProp eliminates into S prime and G eliminates into S prime. Morally, well, here G is some kind of ground sort, and yes, you can have any conversion rules you want on this ground sort. And maybe, well, the conversion rules of G and SProp are not compatible. And so, yeah, we cannot instantiate S prime to SProp, nor can we instantiate it to G. The second case is that, yes, maybe we have a sort S prime that eliminates prop, and we have two other sorts, type and G, that also eliminate prop. So what should we instantiate S prime with? I mean, type or G, both, I don't know. So in the first case, what we do is that we require S prime, or I mean every sort variable in the elimination graph, to be dominated in the graph theoretic sense, which basically means that there can only be one thing directly above. So yeah, if we remove the elimination from SProp to S prime, then S prime is dominated by G, or if we remove the elimination constraint from G to S prime, then S prime is dominated by SProp, and if we add a constraint from prop to S prime, then, well, S prime is still dominated by SProp. And on the other side, well, what we can do is actually have this initial sort that was proposed to say, OK, we have data that eliminates into everything, and then maybe, and then here we can say S prime can just be instantiated by data. So let's come back to this theorem. Now, how do we instantiate the sort variables? So first, we have to ensure the existence of the ground sorts that directly above every sort. And so, yes, and we also need to take care of strays and so have this initial sort data. So in this case, well, what we can do is simply instantiate every sort variable by taking the dominant ground sort, so the sort that's directly above every sort variable, and use the initial sort if there are no such dominants. And I mean, this doesn't actually conclude the proof, but there are some gory details that I'll spare you. And so what we actually did was that we made that a reality in the Rocq proof assistant. And so, yes, actually, there is way more than what I told in this talk, but the main point is that if you want to follow the integration of elimination constraints and actually be able to use sort polymorphism, you can follow the RFC. And I mean, some of the stuff has already been integrated for Rocq 9.2. So we have a small manual prohibition of SProp eliminates to S that we cannot do at the moment because, well, conversion issues. And yes, we also have elaboration to get the principles of assignment and to avoid all of these annotations that's a current PR. So there is some downside is that we have a bit of regression even in the monomorphic case of performances, because instead of checking eliminability through a static table, we do it through a graph. So yeah, we lose some time with this, and we have some bigger structures during the elaboration and all of this stuff. And so to conclude, what we have done is to extend the type system of sort poly so that we have relative consistency with the system, actually the same logical power. We have also principal sort assignments and an elaboration procedure that yields this principal sort. And what we want to do in the future work is to adapt the tactics and libraries to use this system of bounded sort polymorphism and to explore a bit more of the meta theory, for instance, with co-eliminability and conversion, and also probably add support in other proof assistance. Thank you.
Thank you very much. Do we have any questions?
So you said that you need a domination constraint to manage to prove the theorem.
Yes.
But is it the case that if you don't have the domination constraint, then the theorem is false?
In general, yes, I think so. Yes, I don't have an example right now, but I think I do.
In your presentation, you said you need the initial sort data to make it a unique like predecessor. So is this data compatible with existing code bases? So if you infer the data as an assignment, should you reject it, or should you because you don't really have something data sort, right?
Sorry, can you repeat, please?
So you say you need to add an extra data sort to make it work. So if like your infer assignment with a data sort, so how it corresponds to like current Rocq code bases, because you don't really have this data sort in any existing code. So like if you infer this, should it be rejected or?
Yes.
Oh. So it's like an arrow sort in some sense.
Yes.
Like, okay, thank you.
Okay, I think there are no more questions, in which case we'll thank the speaker. Thank you very much.